Welcome to a presentation of neural machine translation for mathematical formulae to be presented at ACL 2023. I am Felix Petersen, and this is joint work with my collaborators Moritz Schubotz, Greiner-Petter and Bela Gipp. So, why are we interested in mathematical formula translation? If we have a typeset mathematical expression, like for example x in parentheses subscript n, the meaning, that is the content of the expression, is ambiguous. In the field of special functions, the notation denotes the Pochhammer symbol, that is the rising factorial. However, Pochhammer himself used the notation to denote the binomial coefficient. To complicate matters further, in statistics and combinatorics, the notation is used for the falling factorial. This means the meaning of the notation heavily depends on the context and is often ambiguous. To disambiguate notations and also allow for mathematical computation in computer algebra systems, there are also unambiguous forms of mathematical notation. Specifically, in addition to the ambiguous LaTeX notation, in this work we also consider semantic LaTeX, an extension of LaTeX developed at NIST to unambiguously denote mathematics specifically for the field of special functions. Further, to allow for mathematical computation, we also consider the notation of the computer algebra system Mathematica. We refer to ambiguous languages for display purposes, such as LaTeX, as presentation languages, while unambiguous languages are referred to as content languages. To explore some other ambiguities, let us consider f and x in parentheses. Here, the notation may either refer to x as a function or mean the product of f and x, which is dependent on the context. As another example, let us consider the sum of I squared plus I. We focus on mathematical formula translation from ambiguous presentation languages to unambiguous content languages. Specifically, first we consider the translation from LaTeX to semantic LaTeX. For this we use the DRMF dataset of over 11,000 formulae. Here, the functions are mostly special functions and are relatively complex and have an average length of 145 LaTeX tokens. As a second task, we consider the translation from LaTeX to the Mathematica notation. Here, we consider the mathematical functions dataset from Wolfram, which has over 300,000 equations. Translating long equations from LaTeX to a content language is a very challenging task due to the extreme precision required by the translation. Getting a single token wrong will often lead to an incorrect result. To achieve neural machine translation, let us consider some neural architectures. First, we consider sequential RNNs, however, due to the length of the equations and the precision required, they were not suitable. Second, we consider recursive tree RNNs. While these performed substantially better than sequential RNNs, they still struggled preserving the content of the equations. Third, we consider the popular transformer architecture, which was quite successful with an exact match accuracy of up to 50%. Finally, we also considered a convolutional sequence-to-sequence model, which achieved exact match accuracies of over 90%. The reason for this is that due to the specific architecture of convolutional sequence-to-sequence models, they can reconstruct the input flawlessly and express the identity trivially. As many tokens are preserved in a one-to-one mapping, for example a division operator, a variable name, or a constant, this capability of information preservation and only changing what needs to be changed is crucial. We would like to remark that it's plausible that our results could also apply for translating between programming languages, as there are many similarities and Mathematica is in fact an application-specific programming language. After discussing the architecture, let's proceed with the evaluation of the results. First, we consider the quantitative evaluation of translating from LaTeX to Mathematica. Here, we consider the exact match accuracy because even small variations can greatly impact an equation. Second, we consider whether Mathematica can import the produced function at all or whether it throws an error. As LaTeX expressions were generated via the export functionalities of Mathematica, we consider the performance of Mathematica when importing those equations again. We found that only 2.7% were exactly correctly imported and 11.5% of the LaTeX expressions threw errors when importing with Mathematica. In comparison, our convolutional sequence-to-sequence model achieved 95.1% exact matches and only 1.7% of the predictions couldn't be imported by Mathematica. Second, we evaluate our model on both the translation to Mathematica as well as the translation to semantic LaTeX. For the translation to semantic LaTeX, we achieved 90.7% exact matches. For a qualitative evaluation, we start with a simple equation displayed in blue. On the left, we can see that, when importing the equation into Mathematica, it is interpreted in a display style as sigma with a subscript k. In comparison, when translating using our model, it is correctly interpreted as a divisor sigma, which also corresponds to the correct original Mathematica expression. Here, Mathematica used a more conservative translation, which however only maintained the presentation information and not the content information. For a second example, let's consider a somewhat more complex equation. Here, Mathematica throws an error and cannot import the LaTeX expression. At the same time, our model correctly translates the expression into the Mathematica format and extracts all relevant information, including the fact that there's a Bessel J, a hypergeometric function, and the gamma function. Thank you very much for your attention.